Hi, in this video, we're going to take a look at using support vector machines in supervised learning. All right, so support vector machines in academics in the classroom is one of the most popular machine learning techniques. Support vector machines are really cool in that they pull in geometry into supervised learning. It isn't very often in machine learning that we actually get to do any really like formula mathematics. We can write it pencil paper math in our machine learning. Support vector machines, we can. And here, this is one of the few times that we really get to pull in geometry instead of like other techniques from mathematics to achieve our goals. All right, now, so support vector machines are, they can handle classification and they can handle regression. Either way, from my personal experience, they've never really been like the winner when I've gone out and I've done my personal projects. Right now I'm working on a project for classification, and in that I'm ending up that I have support vector machines is about middle of all the models that I've been building. That's a raised basis. Radial basis function is my kernel on that. All right, so actually what I want to jump to first before I get into my Jupyter notebook, I want to talk about what's going on with the hyperplanes and the geometry of support vector machines. All right, so I'm using scikit-learn. This is in their help documentation. Actually, they'll show you the web page. Make sure I give credit. Right here is the website to go to. All right, and so here, let's say that I've got two predictor variables and I have a classification problem of 0 or 1. And the zeros are represented by purple and 1 is represented by yellow. And I have my two predictor variables as my X and Y uh, dimensions. All right, well, what we're going to do, I'm going to try and come up with a split on the data so that we get all the zeros on one side, all of the ones on the other side. Now, if I was to go and do this so that let's say that I absolutely have to have 100% guaranteed have to have perfect separation. Well, looking at this, I would probably like slice here. Let's say, let's assume I have to have a straight line for first argument. Slice here, and I would see that I would have purple completely by itself, yellow in this upper right-hand region, and yellow in this lower region. And the region over here, if I slice, I wouldn't know what's going on, honestly. Um, it will that would end up overfitting. All right, what's going to happen if I go through and I start slicing with hyperplanes through the higher dimensional space and I make it so that I have perfect classifications? I'm going to over partition the space and I'm going to overfit. And so what we're going to do, we're going to allow a little bit of error in my classifications as I slice through. All right, so I'm going to scroll down to the linear basis. I've zoomed in so everything's like really, really big. Let's see if I can get this on the page. Yeah. All right. So here, there we go. All right. What we're going to do, once again, I want straight lines to go through and chop up the space so that I can classify. If it's on one side of the chop, I'm going to say it's 0 or 1. On the other side, I'll say it's the other one. All right. So what we have for the linear kernel on this one went through, and here is the decision boundary. All right, so here's my decision boundary. Now you'll notice something that's important is that this is not a perfect classification. You'll notice I've got yellows. The model says everything over here is yellow, but it got it wrong over here. It says that everything on this side of the chop is going to be purple. Okay, and so this is not an overfitting model. It's not perfectly accurate, but I think it would do well. Now, these dashed lines here, these are identifying which points are closest to the decision boundary. So this is where the support vectors come from. This purple here is the closest purple in the purple region to the decision boundary. And along here, I'm maybe one or maybe one, two or three. I don't know the exact details. I'm just eyeballing it. But these three look like they're going along the support vector. These are the closest yellow to the decision boundary, and this is where we get our support vectors from. These dashed lines. Okay, so well, what I've gone through, I've done hyperplanes. Well, from a math perspective, what I could do, you know what? I could actually take this data. It's right now, it's two-dimensional data. Let's say I map it to a higher dimension space, and then I go through and I find ways to cut in that higher dimension space, and that will improve my classification. Then I bring it back down to the two-dimensional space. I can do that. I can do that very easily, from a math perspective. Um, what we're going to call the kernel trick. The kernel trick is it's like the dynamics diagram. So mathematically, what I do is I take two-dimensional data, take it up to higher dimensions, figure out the partition that works in that higher dimension space, then map that back down to the two-dimensional space. All right, and so we've got a little bit of a process going through, but there's a trick. We call it the kernel trick, that using some mathematics, I can actually just go ahead and skip straight to the result I want without having to go through that higher dimension, figure it out, and map back down. I can just do it all in one step, and that's called the kernel trick. All right, so if I scroll down, so what we looked at before was the polynomial kernel, or sorry, the linear kernel. Now we're looking at the polynomial kernel, and you'll notice now that with the polynomial kernel, my decision boundary curves out here, and we can see now we have a perfect classification. Now, if I look here, I mean, this is kind of a wide swinging out for one point, right? So this may be overfitting. I don't know. We don't have that much data, but I would be concerned about overfitting off of this, that in this region here, I would be concerned. And now notice that with this polynomial kernel, my support vector is curving also. Support vector is curving, and the decision boundary is curving. Now, if I get to the next one, now this is the radial basis function. This is the default kernel in scikit-learn. So we're using E. We're using E for this one, and you can see that I have even more flexibility in what's going on compared to the other two kernels. And in fact, what it's done is it said, hey, I've got islands of yellow, everything else is purple. All right, that may be right, that may be wrong, I don't know. But this is what the model is giving me. And you notice that my support vectors now look very, very different from what they looked like before. Now, the next one uses hyperbolic tangents, the sigmoid kernel. And you see that here things are going kind of, it looks kind of crazy. And you can see that here, it really didn't do a good job on picking this up. It's saying that, these are yellow, but they're in the purple region. That's a mistake. This is yellow region, but I've got purple in here. That's a mistake. Got purple in here. So this one really didn't perform that well, but it's a tool in our tool belt so that we have that option to work with. Let's see, I think that's it. Yep, that's the end of it. All right, so now let's get back to my notebook. All right, so support vector machines is a class of supervised learning algorithms used for classification and regression. They aim to find the hyperplane which best divides the dataset into classes. This method is particularly useful when the classes are not linearly separable. The beauty of support vector machines lies in the utility of geometry and the introduction of the kernel trick to handle nonlinear data. So linear data would be a situation where I could just chop it and get my result straight away. And when it's more complicated, we need to have a more complicated kernel. The support vector machine is a supervised learning method that creates a hyperplane or set of hyperplanes in a higher or infinite dimensional space, which can be used for classification, regression, or other tasks. And so we want to separate the data in such a way that the margin between the two classes is maximized. And so what it's trying to do is get define a boundary where the gap between the closest points and the boundary is as big as possible. The margin is defined as the distance between the separating hyperplane and the nearest data point from either class. A support vector machine aims to maximize this margin. All right, and so here is just the mathematics of just defining the hyperplane, and you realize that this is higher dimension like vectors is what's going on. All right, hard versus soft margin. All right, with a hard margin, I'm saying I have to have perfect classification, and this can lead to overfitting. A soft margin, well, I'm willing to accept my classification isn't going to be perfect to protect myself from overfitting with my machine learning model. So hard margin, this assumes that the data is linearly separable and tries to find a hyperplane without any misclassification. This can lead to overfitting in the presence of noise. Now, soft margin, this allows some misclassification in the hope of achieving a more generalizable margin. To control this parameter, we're going to adjust the parameter value of C. Now, the kernel trick, so what this is doing is that mathematically, I can go through the process of take my data, let's say it's in that 2-dimension space, because I have 2 predictor variables, take it up to higher dimensions, do my hyperplanes in higher dimensions, and then come back down. Mathematically, that's possible. I can do that, but that's going to be a lot of work. That's going to be a process. What I can do instead, mathematically, I can use kernels to just basically just go straight to what I want. I don't have to go through the higher dimension. What this does is that this makes it computationally easier for me to get around these problems of non-linearly separable data. All right, so for the linear kernel, we're really just doing a dot product of the input samples. It is then applied to any combination of data points, samples in the data set. The dot product of the 2 points determines the cosine similarity between 2 points. The higher the value, the more similar the points are. Training a support vector classifier on a linear kernel results in an untransformed feature space where the hyperplane and the margins are straight lines. And so this is nice that I'm not really fussing with it. This is very straightforward. Due to the lack of expressivity of the linear kernel, the trained classes do not perfectly capture the training data typically. Now the polynomial kernel, all right, so we're going to change the notion of similarity. We're going to invoke, well, a polynomial on that dot product here. D is the degree of my polynomial. The default is 3. Gamma controls the influence of each individual training sample on the decision boundary. And R is the bias term that shifts the data up or down. The default is 0. Now, the radial basis function, this is the default setting in scikit-learn, also known as the Gaussian kernel, measures similarity between 2 data points in infinite dimensions, and then approaches classification by majority votes. And so you can see that we have an exponential, we have a coefficient with a negative sign, and then we have the squared norm of the difference between 2 vectors. Gamma controls the influence of each individual sample on the decision boundary. The larger the Euclidean distance between 2 points, the closer the kernel function is to 0. This means that 2 points far away are more likely to be dissimilar. Now, the sigmoid one, this uses hyperbolic tangents. And you'll see, once again, I've got coefficient times dot product plus R. Gamma, the coefficient, controls the influence of each training sample on the decision boundary, and R is the basis term that shifts the data up or down. Think of it like an intercept. In the sigmoid kernel, the similarity between two data points is computed using the hyperbolic tangent function. The kernel function scales and possibly shifts the dot product of the 2 points. And there's also a pre-computed one that's available in scikit-learn. That's for what if you have a specific one that you want to use and you want to invoke that instead of using like the default settings. All right, so what is a support vector machine kernel? A kernel is a function that computes the dot product between two vectors in a transform space instead of explicitly transforming the vectors into a higher dimensional space and calculating the dot product. All right, the kernel provides a shortcut by directly computing the dot product of the original space, which can be computationally more efficient. The kernel is basically giving me the advantages of mapping to a higher dimensional space without doing the work of putting it into a higher dimensional space. The kernel essentially allows support vector machines to create nonlinear decision boundaries without explicitly transforming the data. Support vector machines construct a linear hyperplane to separate data, but real-world data is not linearly separable, almost surely. Kernels help support vector machines deal with such nonlinear data by implicitly mapping the data into a higher dimensional space where it becomes linearly separable. Well, why is this efficient? Well, because I don't have to mess with the higher dimension. And now the choice of the kernel will have a significant impact on the performance of your machine learning model. Honestly, I think you should just pick the one that works best for you. So like go through, do your parameter tuning, and then pick the one that works best. I've encountered people who say, by understanding, your problem, you can come up with which one you should use. That doesn't really tell me what to do when I have new data. I think you should just try it and go for it. That's what I do at work. All right, so the dot product. So when fitting a support vector machine, the vectors in the dot product come from the training data. Let's break down the process to understand this more clearly. If I have a training data with 1,000 rows and 5 columns, each row represents an observation. Each column represents a feature or dimension of the observations. When we compute the dot product between two observations or vectors from this data set, you're taking the dot product between two 5-dimensional vectors. All right, so each row of our data is a vector for this. And as each observation has 5 features or columns. So we're doing row vectors. So when we say support vector machines, when we think of vectors, it's row vectors on this in the standard way of doing a pandas data frame. Support vectors. Support vector machines work by finding the optimal hyperplane that maximizes margins between two classes. The data points that lie closest to the hyperplane and influence the orientation and position are termed support vectors. Only these support vectors are crucial in defining the hyperplane and future classifications. So here's something that's important to understand, that when I go out and actually fit my model, I'm not going to have all of my original training data. I'm not going to have all these dot products stored. I'm just going to keep my support vectors, and then when in the future, when I go and I do my classifications, I consider my support vectors, not the whole kit and caboodle of the whole original thing. All right, so now the dot product in the original space, when you use a linear kernel, the support vector machine essentially calculates the dot product between the support vectors and other data points to determine the position and orientation of the hyperplane. So the dot product in the transform space, the kernel trick, when dealing with nonlinear data, we use a kernel function to implicitly map the data to a higher dimension space where it becomes linearly separable. Instead of physically calculating the coordinates of data points in the higher dimensional space, the kernel function computes the dot product directly in the original space, skipping a lot of work, which corresponds to the dot product in the transform space. All right, so during the training phase, the support vector machine will calculate the dot products or kernel dot products between all pairs of data points to identify the support vectors and determine the hyperplanes. All right, now data prep. All right, this one's actually, this is really important for you to understand that support vector machines are very sensitive to the scale and distribution of the data. Proper data prep is super important for us to get the results that we actually want. All right, so feature scaling. You want to scale your data 100% guarantee. The two major ways is to make sure that you're, all right, so I made a mistake with my latex, but all right, I'll fix that for class. The transform features could be on a scale from 0 to 1. This is a good choice if I know like what's the maximum value of everything. So let's say I'm dealing like with pixels. I've got 0 to 255, and I've got other binary variables of 0 and 1. I've got a whole bunch of things that I'm working with, and I know the minimum value, I know the maximum value that's possible. It's not like it's not something like amount of the temperature on the day that I don't like. In the future, the hottest day is going to be hotter than the hottest day so far. When I have a hard bound upper and lower, it's a good idea to rescale your data to 0 or 1. Another choice, and this is I feel is actually a better choice, is to rescale your data to have sample mean 0, sample standard deviation 1. And so by doing this is standard scalar in scikit-learn. When I do this, I have everything on a similar scale. Now, handling outliers, support vector machines are sensitive to outliers. So especially when I have a soft margin. If I have one data point that one value is just crazy off, let's say there was a mistake in there, and that data point, ends up getting thrown onto from the, gets, thrown into another group that I'm classifying on, it can throw off my modeling. So I need to make sure that my outliers are handled. Data transformations, of course, I want to consider, log transform or Yo-Johnson, Box-Cox. You might want to consider polynomial features. Also, when I'm dealing with categorical data, I have to have 100% numeric data for support vector machines. That's true for any system. And now scikit-learn only accepts numeric data. So no matter, for all model structures, you have to have, like, your categorical data has to be converted to dummy variables. But if I was using a different platform and doing support vector machines, I'm going to have to do dummy coding to do support vector machines. Class imbalance, the same thing for like any other classification problem. We have our techniques of, downsample, upsample. We can adjust weights. That's the best one. We also make synthetic data. Avoid synthetic data if you can. And then, of course, I want to get rid of irrelevant features, just like with any other supervised learning project. Get rid of irrelevant features, select the best ones, and remove collinearity if you can. All right, so I'm going to go through and just show you how to do this. So I'm going to use the mushroom data set once again. So remember, in this data set, the odor predictor variable almost gives you a perfect model in one shot. This is all my data already prepared. I prepared it in a previous video. Here are the predictor variables I'm going to include. I'm going to set up my X and my Y. Notice that this is not partitioned. I have my training X and my training Y. And I can take a look at the distribution. So it's not quite 50-50, but it's close. And 1 means it's poisonous. All right, so now what I'm going to do is I'm going to set it up so that I'm going to have a list of all of my models I'm going to have. All right, I'm going to do parameter tuning. I'm going to have my different kernels that I could possibly use: linear, polynomial, radial basis function, or sigmoid. Here are the different soft margin values I'm going to just try. And then I'm going to go through and I'm just going to create a list of all the models. Now, this is not fitted yet. These are the pre-fitted models that I'm just going to have a bunch of these. And you can see that, so I've got what, 1, 2, 3, 4, 5, 1, 2, 3, 4. I'm going to have 20 different models I'm going to try. All right. Now, something about support vector classification is that by default, I'm not going to have a probability fitted value. If you read the help documentation, it is possible with the support vector classifier that my classification and my probabilities won't always jive. So that's just something to be mindful of. For my work, if I'm doing classification, getting a classification by itself almost never is good enough. The people that I work with, they want to see a modeled probability value going into the classification. And so here I'm putting probability equals true. The default is false. If I leave it on default, I'll be able to get the classification off of there of poisonous, not poisonous, but I won't be able to get a probability of being poisonous. All right. And so here I've got my 20 models. And I'm going to go through and fit each of them. And now you'll notice I'm using list comprehension. I find list comprehension is such an easy way to keep your workspace nice and clean and neat and to iterate over things. All right, I'm fitting the values. And so now let's go ahead and get our predictions. I'm going to skip over this aspect. All right, so if I run predict on each of the models, this is going to give me the classification. So this is going to be either 0 or 1. It's not going to give me a probability. If I do predict proba, then I'm going to get model probabilities. I can also get the log of the probabilities, but for my work, probabilities are almost always good enough. The logarithms of probabilities is most useful when I have very, very small probabilities. Here, that's not an issue. And then I'm just going to keep everything in a nice little neat data frame. So what I've got here, I've got a data frame. And notice I had to do a transpose to get this. Is that this is the first support vector classifier, second, third, fourth, and so on, all the way down to my 20th. Remember that scikit-learn starts at 0. All right, so here's the first one. And so this is model 0. This is model 1, model 2, all the way down to model 19. All right. And so here I can see, I've got my probabilities. So now let's get the AUC. So the AUC is a good way of evaluating how well do I have control over the cutoffs. So where I work, it's not just about the probabilities, because frequently we're going to be making decisions